Hi, everyone. I've been in the industry for 15 years, optimizing water operation for European locations of our high-tech customers. And I'm specializing on high criticality, high reliability, and high automation. And we as a company, Ecolab, work throughout the industry with all names, hyperscalers, and also local players alike. So what do we do? Ecolab is involved in almost every chip from wafer to end user, and the water we manage for the customers is utilized in all operations. As you know, water carries energy, and energy carries information, and our job is to optimize all water utilization throughout the sector for our customers. So basically, we carry mostly the information on the water. And when we deep dive into data centers specifically, water has many uses, and these are typical areas we focus on. We don't start doing that yesterday. We did it for more than 100 years, and we consider the whole water from source to discharge. There are many innovations and best practices we bring as a company to support your business. And for today, I'd like to talk specifically about the direct-to-chip liquid cooling. For those that might not know, direct-to-chip is part of a larger water system, which we should not forget. But today we deep dive into the so-called secondary loop, which is in the white space, so on the data floor. But here you see a picture of the whole system, how it looks. And to be a little bit more graphic, what we see in the white space on the data floor is that we have these servers or nodes exchanging heat through copper or aluminum cold plates to a so-called cooling distribution unit. And that cooling distribution unit is often on the same data floor. This cooling distribution unit exchanges the heat from the secondary direct-to-chip loop to the primary loop to get the heat out of the room. And just for an intermezzo, what I like to do in my spare time is do some beer brewing. And one of the most important things to worry about during a beer brewing process is that you need to keep your equipment meticulously clean to get the best results and also to get a good tasting beer. The same is actually really important in direct-to-chip. As the issues we do not like to see on the cold plates, which are directly attached to the chips, I remind you, some of them could be like scale, biofilm, corrosion, or general fouling. And given these really small fins, often from copper or aluminum, and the large surface area with a low volume of water, small issues can quickly overwhelm the system if not tightly controlled. So when bad things happen, we often see these causes and effects, ranging from coolant degradation, corrosion issues, biogrowth, or even expensive unplanned downtime, and which could lead to repairs of whole blades or nodes. And we can simply not allow these concerns to become issues in operation, not even impacting the performance of the system, because as chips get hotter, they also often throttle back. Which brings us to the topic of today, how to make direct-to-chip cooling into a success. And we would recommend you 3 goals in keeping things clean. To start off, I will talk a little bit about design clean. So start with the design engineers to examining the potential designs, and water-related challenges can often already be avoided in the design. After that, I will talk a little bit about startup clean, because part of any good installation is a good startup procedure. And instructions for that startup are developed by us to minimize potential problems that can occur. And of course, also in operation, a treatment protocol to maximize the uptime and provide for any environmental and regulatory compliance, and also ease of use for the user applications. So to start with design clean, what we often want you to consider are the metallurgies used, especially copper and aluminum are some of the ones that need some careful and tight consideration. Also the coolant type that you use, if it's a glycol-based mixture or it's more water-based, any type of maintenance equipment that you might have in there. And also related to that equipment, what kind of filtration is already designed into the loop? Have you carefully considered that there is not room for dead legs? And is there any good fill and drain points? It's not only important during startup, but also along the way, if there is a need to top up something or to change something in the fluid, it is important to have these points in the design already. And of course, user-centered, that it is easy to sample, it's good and easy to manage the coolant. And we need to consider we are in a critical environment. So there is no room for leaks or mistakes or errors. And we also need to consider that the access to these environments are often heavily restricted. So it's not easy to bring in equipment or bring out equipment. And that's also something we want you to consider during the design phase. And then for startup clean, as you might know, these projects have quite a strict timing quite often. But it is important to consider what if there is a delay in some part of the system? Is everyone involved? Can we work around this? Are there alternate options? Also in terms of suppliers for chemistry, do you have second options or alternatives? How to manage that coolant? And also what to think about the materials when they are in storage before you even build a system. How do you handle that? Of course, good resources are important. So the water quality that's coming to the site, the kind of pre-treatment or equipment that you use to make the water suitable to be used in these loops. Any recirculation you employ and testing of the water. And also the pre-flushing. And it must be said that these loops are not a typical closed loop. It's never that a closed loop is typical. There are not two alikes. But you must consider that you should have multiple sample points, and the conditions might change from one point in the system to another point in the system. It is important to do phase verification of the system when you employ it and hook it up and start it up, and that you consider the whole system and all its cannies and crooks when considering the cleanliness. Also, in terms of quality control during operation, it is important that you need to consider what happens there. So what we see is customers exchanging blades because of lifetime, because of other concerns. So IT swaps, equipment swaps. And then the question often arises, who owns the loop and who owns the liquid that is inside these loops? This gets more tricky when you are a co-locating facility and your end customer is managing part of these tasks or equipment. So you must consider that in a good operation environment. How are we handling cleanliness there? How are we handling pollutant? How do we check for materials entering and exiting the system? And what we want you to consider is also early detection is really important. So quality monitoring of the coolant employed is so critical to keep the loop tidy and nice and clean and in good working condition. We did an audit of around 200 cooling samples that have been analyzed by our lab. And we actually found out that 79% of these samples were out of spec on one or multiple parameters. And this highlights also the importance that just taking a sample once in a while might not cover it for your facility. These loops are under a lot of stress. They do see a lot of cycles. And even with the increase of AI and machine learning, what we often see is that these systems are operating in a peak load with some idle time, with a peak load again. And then it gets especially important to have some maybe online monitoring equipment in there that tracks the condition of the coolant, that tracks the state of the coolant if it's not degrading, and also manages to track some early warning signs for example, bio or corrosion. It's important to also minimize the coolant loss, not just because out of an economical perspective, but what we also often see is facilities that have environmental constraints because of the stuff that's used within the coolant. You need to have a smart sampling plan there. You need to have good maintenance practice and also the options to boost. And what do I mean with boosters? What we often see, for example, is that anti-corrosion inhibitors are being depleted over time by the system, especially when you have new systems or you have systems where there is a lot of IT swaps and changes, that some parts of these coolant inhibitors just run out. Same thing can happen with biocidal chemistries used, that you run out of sufficient strength of biocide. And you need to be in time to prevent issues from happening there. The earlier you are, the better it is, the more problems you can prevent. So these are important things to consider when in operation. Of course, we're not alone, and you are also not alone. What we often do is that we work with the industry to collaborate and to drive success, and also to share common knowledge and learnings. So what you could do today already is check out some of the materials that we have publicized, for example, with the Open Compute project, on how you should start up a loop, how you should flush a loop, what are considerations when using propylene glycol-based systems versus what is there in water-based systems. We also do this with ASHRAE, and we're also part of the IMASons, where it's also important to consider that the chemistries that you employ are safe to use and also not under environmental constraint. You can find our contributions under the name Nalco or Ecolab on many of these platforms, and we invite you to download them there. Often it's for free. Of course, our team of 48,000 people is ready to assist you everywhere on this planet, no matter if you're designing a system or starting up or operating any system. And it also doesn't matter if it's a water or a glycol-based system, we can support you on that. And yeah, for this, I would like to open the floor to if there is any questions.
Thank you, Andres. We did actually have a question on the first point that you made about how you brew your own beer. John Side says, "Is your beer actually for sale?"
No. That would be competing in a big market here. So I'm based in the Netherlands, and as you may know, we have quite a competition here on beer brewing. So it's not for sale. It's just for private, and it's just for our own, just to learn and to play with these systems. And it's nice because it's a complex interaction between biological, some chemistry, a lot of personal taste also. And you learn a lot about equipment and heating and cooling. So this is one of the things that I just bring my work over into my hobby and vice versa. I hope that
There you go.
answers the question.
Yes, thank you. And I actually have some questions regarding your day job as well. Firstly, how do pre-commissioning practices impact day one performance and long-term reliability?
Well, the pre-commission is massively impacting, and talking from experience, materials have different timelines when they come to site. I shortly highlighted that, and what we often see is these materials are not tightly controlled during shipment or during storage. Sometimes the timelines in these projects, they are shifting. Sometimes it's not really clear who's owning these materials and where they are. And what this could cause is most often corrosion and plugging to occur. And when we do root cause analysis as an auditor, which we can also support with our lab and analytical capabilities, we often note that problems could have been prevented if more attention is paid on that pre-commissioning process. One of the examples you could do is to do a careful flush out of the system before you start it up, especially if you're not entirely sure of the state of the materials when you employ them in the system. And then we can combine it with some monitoring to see and to track what's happening there.
Excellent. We do have a flurry of questions that have just come in from the audience as well. Andrews, as hyperscale operators push beyond 100 kilowatts per rack and start using hybrid dielectric and direct chip cooling loops, the water chemistry regime becomes far more sensitive, not just to conductivity, but to microbiological stability and mixed metal corrosion in secondary loops. From your
Yes.
perspective, how can operators realistically maintain chemical stability and corrosion control in closed, low-flow water loops where evaporation is minimal and oxygen ingress is almost zero, especially as glycol blends and nanofluids begin to replace traditional treated water? It's a long old question.
Yeah, no, and it's understandable because this is the most important bit about closed loops, and we have a lot of experience with this. We work with suppliers from EUV equipment until the suppliers of the chips and the systems that you all employ into your data centers. And we have, this is not new. The closed loop is not new. We have seen it in high performance computing before. We support a lot of systems in that, and indeed, yeah, hyperscalers are now moving towards CDU capacities of even 2 megawatts. I think the latest Deschutes design was around that mark. So you have a huge heat load into a small loop and a small system. And yeah, we get more critical. We get closer to the chips. We have seen some designs wherein the water is actually touching the silicon or touching the chip. And what we also see with those shrinkage is that there is more surface and smaller channels. It gets way more important what kind of corrosion inhibitors you use. And there, I must say, there is a lot of good options in the market now of corrosion inhibitors that are not only strong and stable, so they don't deteriorate, but are also not causing any biogrowth. Because what we often see is it is a matrix where you try to prevent corrosion, but you actually add a component that might lead to more biogrowth or more biodegradation. And one of the most important things there that we can mention is to do that online monitoring, and there are solutions for that. We also offer solutions for that to keep track of what's happening, if there is enough in there, if it's still active enough, and if it not has been degraded. Because even simple propylene glycol, I call it simple, but it is complex already, is prone to degradation over time. And this is something you can track and you can monitor, and I think you should do that. Combined with, of course, also lab testing, because there are some things we cannot measure in the field, but most of the things we now have capability to measure online and in the field. I hope that answers the question a little bit.
Thank you. John said great answer. So I think you definitely answered the question. What are some common, you mentioned testing there. What are some common hydro testing mistakes that can later lead to contamination or biofilm?
So what we see in the startup of these data centers is that you want to go through a checklist to check for any leaks, for example. And what we often see is that they use a water source to pressurize the whole system and check if there is any leaks. And then because you don't use already the chemistry in there, but you often tend to use just water, because the thinking is then if we just use water and there is a small leak, it's easy to clean up and easy to contain. But what we see here is the main issue is that they use an inadequate quality of water. For example, they just use the potable water that is coming to the site. And that could lead to rapid pollution, not only with bio, but also with scale and other compounds. And we need to remember that drinking water has been designed in such a way and has been processed in such a way that it is just suitable for us to drink and to consume. We will not die of it, but it is not made from a standpoint of corrosion protection. It's not made of an anti-bio protection. And you won't see biocides in your drinking water. So yeah, what we see is that is one thing. And also if you then say, well, let's drain after the hydro testing, it also needs careful consideration, because this is often the moment where we see oxygen ingressing into the system, or we see a lot of pipelines that are partially filled with water, which leads to really strange corrosion, or not strange, it is logical and explainable, but it leads to corrosion in these pipes where the water level is. So that is quite important, yeah.
Amazing. We have another question from Graham. What is the difference in cooling footprint for this and the air-cooled environment, and how does this affect the business plan for a data center build?
Well, it is a way higher density of power on the data floor. And don't quote me on the numbers, because it is rapidly evolving. And I do have some numbers, but some of them could be confidential. So please look them up online. But what we see is the power density is increasing. So there is more kilowatts per square meter employed, and you can handle it because the air is not longer the limiting factor. What used to be in the data centers is that moving the air around in a quick enough and with a high enough mass flow rate will lead to issues due to pressure drop and etc. It is shifting also because of that. Water has the capability to take a lot of heat out of your system because it has that tremendous heat capacity. And often you can support it on an existing system. What some of the things we do want you to consider is that if you retrofit it into an existing data center, what you see in modern designs of new data centers that have been built for direct-to-chip is they use overhead lines to get the water on the data floor and remove it. What you then see if you have a retrofit is that it is often employing the lines below the floor that have been designed for air handling units. These lines could not be sufficient in capacity, and they also often quite lack the required fill and drain points to make it into a good system. So yeah, these are some of the things we would like you to consider. Again, a lot of the information is open, is public. Many of the industry providers work on that. I also see most of the sponsors of this conference all collaborating and participating and sharing that knowledge. So would really love to invite you to read up on it on, for example, Open Compute project. Yeah.
Amazing. I was actually just about to ask you about retrofitting, and then you answered my question. Anyway, thankfully we got more audience questions. How do you distribute to avoid a single point of failure?
Well, often redundancy is again a key word in here. It is employed redundancy within the system, but it is mattering on what level. What we often see with hyperscalers is that the redundancy is more in a bigger picture, and they aim for high reliability, but they allow for certain parts of the system to drop out. Of course, that's not something you can do as a co-locator. So what we do see there are some A/B tactics, but it is difficult because this water will directly hit the chips and hit the coolers on the chips. And I have yet to see chip designs or cooler designs where you have two coolers supporting a single chip. And that's why that managing that water is really critical. One of the tactics often employed is to lower the risk by having somewhat smaller loops. We're pushing the boundary already with the 2 MW loops there. But this is one of the tactics you could employ. And of course, have valves in there. I see from all the providers having good valves in there that even have quick disconnects that make it easy that if there is an issue that you can isolate parts of the system. And this is also so important from a design perspective that you take due diligence there, that you design for that.
It seems like questions keep coming in thick and fast as quickly as you can answer them. Um, how scalable are flushing slash skid approaches for hyperscale versus small edge sites?
Well, the procedures we wrote together with the major partners, as can be found, for example, on Open Compute project, have designed with any scale in mind. So we took great care to design these procedures that are matching hyperscalers and also, for example, the smaller edge sites. There is, of course, some difference. Diameter of piping, that may lead to additional considerations. There is some difference in surface area versus volume. But we can recommend, for example, to close valves of certain sections during initial recirculation and flushing, especially to prevent debris from larger piping to fall into smaller loops. As with anything, when in doubt, please reach out. We support any skill, and we always have someone close to your site. But yeah, if there is material that you need, you can find it online. Just find our name.
And what are 3 practical actions for an engineering manager planning a first direct chip deployment, would you say?
So again, starting with what I said last, first, please read literature.
Yeah.
Guidelines are there and they're written to be easy to read. They change often. We often revise them. And there are your biggest chance to successful and timely deployment. For 2, I would say, please select a competent company that oversees the quality of deployment from the water perspective. Don't trust your builder to take that into consideration without mentioning it. At least discuss it with them and check if you can bring on additional resources to just keep things in check and ask the right questions and see if things are done according to procedure. And then the last point, I would say the first days and steps are critical. Successful deployment and also the monitoring from day one will save you a lot of trouble. It will give you the most reliable, efficient, and also economical system. Because if something is amiss, quick actions are always better than to wait. Same as with beer brewing, the biological issues, they don't get better if you wait without any action. And same thing can be said for corrosion. If you just let corrosion happening and take its course, it's not going to improve on its own. So and it gives you also the opportunity to make small adjustments early to combat it instead of needing to take the big guns to fight your problem.
Well, Graham rather jokingly asked that, given its purity, would your beer work as a good coolant?
I won't. I don't think so because there's. I do employ some filtering, but I like to have some amount of yeast there still in, and I will. That will for sure cause clogging. Now, and also if you heat it, it will lead to scaling and fouling. These are things to consider. We also see it, for example, with polymers that come from the tubing inside these servers. Same as the polymers that are made by the yeast to establish itself. They are quite alike. So it is important to consider the right water quality and the right things that are in there or are not in there. for building these loops. And that's what I really want you to bring home as a message is please mind water quality. It's so important and so critical to the system. It's never easy, but if you bring the knowledge and you bring the experience, it can be made into a way easier and an easy startup and also easy operation for many years.
Amazing. Last but not least, unless we get another question in between now and your answer, in terms of leak detection, which technologies are leading the marketplace for direct chip within the high density rack area? And what solutions do you think are needed to help future proof these high density racks for leaks?
Well, this is an interesting question because I see multiple approaches there, ranging from pressure monitoring to solid leak detection with wires across the floor or even floating valves. We in our own skids, we employ multiple of these systems together. So we keep track of multiple parameters to check if there is any leak happening. And indeed, yeah, it is tricky because what's happening with water when it heats, it changes, it expands, it contracts. Also, the whole system is expanding and contracting based on flow rates. So it tends to be inaccurate to just check pressure, for example. And also, often many of the circulation systems are working on a fixed pressure set point. Some good things that I do love and do like to see in systems is mass will not change or leave or disappear. So what one of the things is that could be employed in, and we do see that in some good CDUs, is that there is an accurate monitoring of the level of water in the reservoir, and that there is a careful keeping track of like what's happening there. And together with leak detection that is near critical points on the floor, that will bring a lot of help and aid to your system. But first and foremost, I would say design. It is so important and so critical to select the good components, select the right suppliers, and select stuff that is made for the job, and not go to the local hardware store to find a fitting that might fit your system. These will fail over time, I can promise you. So please consider that.
And I thought I'd be able to let you go, but we did just get another question. If you're taking the fluid to the chip, can you shut down quick enough to avoid damage at the chip if there is a leak?
Well, it depends on the leak, because if the leak is directly affecting and going onto the electronics, well, that's of course worst case. But in terms of the heat load is not being removed, what we do see in many of these designs, they are carefully monitoring the chip. And if the chip is sensing that its temperature is increasing, it will often internally already throttle down or even shut down. What I would say here is that it is important to have monitoring also around the chip in terms of temperatures and flows, and do something with that monitoring. Employ limits. Be alerted if something is running out of spec, if something is out of the norm, because the earlier you detect, the earlier you can stop things, and preferably make these things automated. It of course depends on the workloads, because you don't want to have an unexpected shutdown because of an alarm that was not really there, have false positive. But these are things that you should track, because indeed the worst thing to happen is for the whole system to run dry. What is aiding with water, what it will do is will evaporate. That will also take a lot of heat, so you get a sudden peak in pressure in part of the system. But yeah, it is important to keep track of these parameters and then to shut down early and on time, or throttle back the load on that chip.
Amazing. Thank you so much, Andries, for answering that avalanche of questions that you got at the end there. Really appreciated.
I'm happy. I'm there. This is my job. This is what I love. Please shoot any questions that there might be, and we'll try to help you or reach you out to the partners that can do. We're in this sector together, and we all need each other to make this into a success. So thank you.
Really appreciate it. Thank you again, Andries.